Attending this CppCon, you will be at a level which you haven't experienced and which you haven't ever have thought of. You'll come to learn about many things which haven't been exposed to you before. So I'm sure you would love to be here, and once you experience this, you'll be like, I want to come next time, and you'll not miss this again.
Hello everyone, my name is Sergey, and today I'll be discussing how to enable Constexpr STL containers that use dynamic memory. You might be asking, Constexpr STL containers? STL allocator and some STL containers is already Constexpr in C++20, what's the novelty? However, it's not quite that simple. Although STL allocator is Constexpr enabled, it has limitations. And the primary goal of this work is to overcome these limitations, allowing us to utilize existing Constexpr STL containers with dynamic memory as full-fledged Constexpr objects. So, what's the plan for today? We will begin with a brief overview of Constexpr, current language features, relevant proposals regarding Constexpr and STL containers, accepted, work in progress and rejected, existing Constexpr containers in the standard library and their usage. Next, we will analyze the challenges, and then we will define the problem and demonstrate how to implement a Constexpr allocator to create fully functional Constexpr STL containers that use dynamic memory. And finally, I will present the results. Let's start with Constexpr. I imagine everyone here is familiar with this keyword, but what does it formally entail? The Constexpr keyword signifies that a variable or function's value can appear in a constant expression. A constant expression, in turn, is an expression the compiler can evaluate at compile time. Primitive constant expression existed in C++ long before the Constexpr keyword. For instance, in C++98, you could write expression containing only integer constants, and the compiler would evaluate those expressions at compile time. C++11 introduced the Constexpr keyword, enabling the creation of Constexpr functions. While C++11 introduced Constexpr functions, they were initially limited, for example, no loops or conditional statements. However, support has steadily improved, culminating in C++20 with the ability to use operators new and delete within Constexpr functions. And finally, in C++26, all containers will be Constexpr. I won't delve into the full history of Constexpr, instead I will focus on dynamic memory allocations within Constexpr. And first let's examine the types of dynamic memory allocation available within Constexpr. Constexpr allocations broadly fall into two categories: transient and non-transient. In transient case, if a Constexpr function is evaluated at compile time and allocates memory, that memory must be released when the Constexpr context ends, that is, the current constant expression evaluation is complete. Consequently, the allocated memory cannot be transferred to runtime memory, static, dynamic, or etc. In non-transient scenario, if a Constexpr function is invoked within a constant expression and allocates memory, that memory can be returned from the constant expression and subsequently used at runtime. The compiler is then responsible for transferring this memory to runtime memory. Generally, there are two types of memory allocations, but what about our favorite language? In C++, only transient allocations are possible as of C++20. Memory can be allocated during constant expression, but it cannot be moved beyond the scope of that expression. You can create a vector within a Constexpr function, but the destructor must be called at the end, releasing the allocated memory. You can also allocate memory directly using the allocator or operator new, but you must release it later. Non-transient allocation is impossible. If a Constexpr function returns a vector and you attempt to create a Constexpr object of type vector by calling this function, it's not possible. Whether you try to return a created object from a function or create it directly using a constructor, the result is that you cannot save the vector as a standalone object outside the Constexpr function. Also, it's impossible to allocate memory via both the allocator and operator new. Here we see that a vector is Constexpr in both cases, but its applicability is limited. And to differentiate these cases, proposals regarding Constexpr memory allocations introduce a special term, top-level Constexpr object. In the second case, studVector is a top-level Constexpr object. And when I initially said it's impossible to create a stud container with dynamic memory as full-fledged Constexpr object, I meant it's impossible to create stud containers that use dynamic memory as a top-level Constexpr object. In the latest language standard cpplusplus we now have two Constexpr containers that support dynamic memory allocations, studVector and studString. So how was this all introduced into the language? The main proposal was P0784. It introduced several key features. The operators new and delete as well as studallocator become Constexpr. It allowed to use of Constexpr destructors. It also allowed Constexpr placement new, though not directly, it's done via stud construct add. Following this, the other proposals introduced Constexpr support specifically for studString and studVector. There were also secondary proposals, for example, one allowed to use of try-catch blocks in Constexpr functions. This was necessary because some functions in studVector contain these blocks. This list includes only the proposals essential for implementing Constexpr studString and studVector, though there were others. Now some new proposals were accepted just a few months ago and will be part of C++26. P3372, this proposal allows the use of all standard containers within Constexpr functions. Essentially, it marks all containers methods as Constexpr. It also introduces limitations on container implementations to ensure they will compile in Constexpr context. P2787, this one doesn't add new features. Instead, it allows to call a constructor on an address not just with stud constructed, but also directly with the placement new operator. P2738 Constexpr cast from void pointer. The name is quite descriptive, I believe. Before C++26, casting from void pointer was impossible in Constexpr. In C++20x it will be possible, but only if the original type stored in the void pointer is interconvertible with the type you are casting to. Conversions between unrelated types are still not permitted. P2686. This proposal enables the use of Constexpr with structured bindings. Compilers generate a lot of code using structured bindings, and Constexpr didn't work with it before. In the new standard it will. P3491, it proposes introducing special built-in functions for defining Constexpr strings and vectors. Originally these functions were part of a reflection proposal, but later they were separated into another one. These functions help to define Constexpr strings and vectors, and honestly, in general, they address the challenges I attempted to solve. However, they were only approved in June after I had submitted my application. And I would like to demonstrate how to tackle this challenge from a different perspective, since these functions have certain drawbacks. They will only be available in C++26. This means it's necessary to implement specific built-in functions for each container that constructs such a container in Constexpr context. They do not work with custom containers. Therefore, I will illustrate how to resolve this issue without relying on new language features. There are also some active proposals. First one proposed to introduce new type, stud basic fixed string. It's a string with local buffer, and buffer is settled and buffer size is settled as template argument. Next three proposals are from one person, Barry Revzin. Maybe it sounds strange, but the first one suggests introducing limitations for Constexpr allocations. The author provides examples of Constexpr functions with memory allocations. These are related to the new reflection syntax. He shows that in some cases it's not necessary to allocate memory at compile time, but if I understand correctly, these cases only occur with the new reflection syntax. The next two proposals have almost identical names and goals, but their implementation are quite different. They propose to introduce non-tranched allocations. However, there is a problem. In some cases, it's not clear when we need to free memory at runtime that was allocated at compile time. Now let's look at an example from the second proposals. The third one has similar examples. Imagine we have nested unique pointers. Now imagine it's possible to use operator new for non-tangent allocations, and we create such an object. The dereference operator in a unique pointer returns a non-const reference. This makes it possible to call the runtime delete operator on an object that was created at compile time. To solve this problem, they propose introducing a new keyword, propconst, which stands for propagate const, among other things. This keyword would help implement deep constants. In this case, a nested unique pointer would become const automatically, making it possible to call its release method. But in my humble opinion, this example feels a bit artificial. In C++, there are already many ways to cause problems for yourself. In this example, you could also pass the address of static variable to unique pointer, for example. Then it would also be possible to call the destructor for that static variable at runtime via the unique pointer interface. This seems like a problem of the class interface, not a problem with Constexpr allocations themselves. But I repeat, it's my humble opinion. Additionally, some proposals were rejected. Here we see that proposal P0784 listed first on the slide with accepted proposals is also included here. This is not a mistake. The first version of these proposals was accepted only partially. It initially proposed introducing non-transient allocations, but that part was rejected. There was also a paper proposing a special container stud Constexpr vector. Before I mentioned an active proposal that suggested introducing the type stud basic fixed string. Proposal 0574 proposed something very similar but for vectors, and it was rejected. Instead, paper with intriguing titles were published as a counter to these proposals. One title was changing the attack vector of the Constexpr vector. The authors of this paper suggested rejecting the proposal for the Constexpr vector. They argued that the Constexpr vector should be implemented using the special allocator, not as separate type. This allocator should be designed as follows. It works simply. For example, there is a container that allocates memory. Instead of allocating memory on the heap, we allocate it in a local buffer placed in the allocator. In this case, it's not necessary to use dynamic memory at all. Honestly, this is not a new solution. It's widely used. It has different names: buffer allocator, local arena, etc. I will refer to it as a buffer allocator. This principle is applied in various data structures. In the standard library, it's seen in stud array, and there are some third-party containers Constexpr libraries based on this principle. Additionally, there are allocator-aware but non-Constexpr data structures. And here we see std_string. However, I previously mentioned that it's impossible to create an std_string as a top-level Constexpr object. This is not a mistake. Why? Because you cannot create an std_string as a top-level Constexpr object if it allocates dynamic memory. But std_string uses small string optimization, which is in fact a local buffer. If the string is small, it is compiled. If you tried to use std_string as a top-level Constexpr object and your code compiled, you were just lucky that your string had the appropriate size. Now let's finalize the overview and primary conclusions. First, the language currently only supports transient Constexpr allocations. If we want to create a top-level Constexpr object, we should use a local buffer. In the standard library, this method is used only by std_array. Here we see that the problem with memory allocations in Constexpr is resolved by a local buffer. However, using a buffer has a problem: the size of the buffer. In the most primitive case of using container with a local buffer, we define the buffer size explicitly. It's not convenient, and this problem can be solved. It's possible to deduce the buffer size from the initializer. I hope that most of the audience is familiar with the function std_array. It works simply. It is a template function that takes an initializing array with size n as a parameter. During template type deduction, we obtain the size of the initializer, which is then passed as template parameter to the type with the local buffer. However, this works only in trivial cases. I will cover those non-trivial cases later. There is also a more universal way to determine the buffer size. Calculate it in two steps. First, we calculate the buffer size. Second, we create the object. For instance, consider the type fastPimple from library userware. It is a structure that implements the principle of pointer to implementation. The structure uses a local buffer instead of a dynamically allocated object. To define the buffer size, we intentionally create compilation error, where compiler print the buffer size, which we then use as the actual buffer size. It is also possible to calculate the buffer size automatically. Just implement a function that calculates the buffer size and call it first to define the buffer size. In the second step, create the final container and buffer with the appropriate size. However, even this method doesn't work in common cases. Let's look at some examples. For example, we want to use an allocator with a buffer in a vector. We create this vector from the initializer list and expect the memory allocated by the vector to equal the initializer list size. However, we know that a vector has two features, size and capacity. Vectors can also allocate memory with reserve. Therefore, it's impossible to clearly determine the buffer size by the initializer size. In the next example, people often ask about standard containers in interviews. One of the most frequent questions is what is the asymptotic complexity of operations like inserting, deleting, and accessing. However, they often overlook another important question. What is the asymptotic complexity of container creation? This is an interesting question. If we examine the constructor for std_vector, which takes an initializer list, we find that it has linear complexity. There is also a note that there will be only one allocation. In contrast, the constructor for stud_unordered map, which takes an initializer list, has linear complexity on average and quadratic complexity in the worst case. Why does this happen? Let's look at the implementation of this constructor, for example, from Clang Sleeps to C++. It just calls the function insert and passes the range to it. The function insert appends elements in a loop. However, each append to the table can potentially cause rehashing and reallocations. This explains why it has quadratic asymptotic complexity in the worst case. What does this example show? In common case, the creation of some container may look like this. Initially, the container allocates memory, then it releases some of this memory. And if we want to use a local buffer for this container, it's not obvious what the buffer size is. At the end, it left one amount of memory, but in the intermediate state, it uses another. And how to calculate amount of memory in the intermediate state? That's open question. And let's analyze the creation of stud_unordered map from another angle to analyze the last example. We pass an initializer list to it during construction. We expect that the constructor of an ordered map will create the same pairs in the heap and store them. However, it's necessary to store pairs as separate memory blocks to support the inserting and removing operations that run in constant time. Additionally, we need to store pointers to these pairs. It's impossible to have a separate member in an ordered map for each pair. Therefore, an ordered map creates an array of pointers under the hood, which stores the addresses of pairs. In an ordered map, there is a separate allocator for this. In fact, there are two allocators inside an ordered map. Many have also used the method extract in associative containers, which appeared in C++17. This method extracts not pair but node from the inner containers data structure. Associative containers do not have create pairs, they create nodes. The unordered map doesn't have a pair allocator. We pass the pairs allocator to the unordered map constructor, but it doesn't have the pair allocator at all. What does this example show? In some cases, we don't know which types of objects a container will create, making the process of calculating the buffer size more non-trivial. So, what conclusions can we draw from this overview of existing solutions and their analysis? I repeat, if you want to create a container as a top-level Constexpr object, you must define where to store its elements. You have no choice, you must store them in a local buffer. Second, if you use a local buffer, you must define its size. In common case, this is not a trivial problem. However, it's possible to create a container in two steps. First, define a buffer size. Second, create the container. So let's create a container with a local buffer using a two-step method. But first we must address the challenges I mentioned earlier. To see how to enhance this method and overcome those challenges, let's revisit the state of the abstract container right after its creation. We must allocate memory. We want to allocate temporary memory on the heap and permanent memory in the buffer. This is possible if we know the script of memory allocations in advance. Let's create the container in two steps. In the first step, we not only calculate the buffer size, we also save information about all allocations in a table. This includes the sequence, size of each allocation, and if it's permanent or temporary. In the second step, we allocate permanent allocations in the buffer and temporary ones on the heap. We can also calculate the buffer size from this table. How does this work? We take the container and change its allocator to one that records information about all allocations. Then we start creating the container. As the container allocates and deallocates memory during creation, the allocator records everything. This is the first step. We keep only the table from it. In the second step, we take the container again and change allocator and change its allocator to one that follows script. We can also calculate buffer size from this script. We start container creation once more. Now permanent memory goes into the buffer, temporary into the heap. But we also need to define the size of the table. So we add an extra step, calculating the table size. We perform the same operations, but the allocator simply counts the number of allocations. We change the container's allocator to 1 with a counter, start creation, and the object is created. We just calculate the number of allocations and pass it to the next step. This is how the overall solution works. I will not show the solutions code on slides because I believe everyone can implement an allocator with a local buffer or one that scripts all allocations into a table. If you want to see the full solution, you can find it on GitHub. I will share the link at the end. I want to highlight just a few key implementation details. And first, let's look at how to exchange an allocator in a container. In other words, we take a container that swaps its allocator, for example, to one that counts allocations. To do this, we break it down into the template and its arguments. Then we substitute the allocator and get the result type. How is this usually done? Rebound classes often have a special template structure to help substitute template arguments. For example, this is used when the allocator has more than 2 template arguments and is applied to standard containers. As I mentioned earlier, an map rebinds the allocator's value. This is how it's achieved. In the structure as a vector, for instance, you get a vector with the same template arguments, but a different allocator. But it's impossible to add such a structure to standard containers. We cannot modify the internal implementation of vector, for example, so let's use a method similar to size deduction for std_array, that is template type deduction. We will use the structure rebind allocator and its template specialization. After template type deduction, the container in rebind allocator becomes vector as the template with t and allocator as its arguments. Then we substitute the new allocator and get the original type but with different allocator. Also, we can overload the structure rebind allocator for other containers that use more template arguments. Note that allocator is always the last template argument in stud containers. It is how its usage looks. Now let's explore passing initialization value to function that implements the creation of Constexpr container with Constexpr allocator. For simplicity, we will use a vector of integers. We have a function make which with a parameter init. As per the earlier described algorithm, we need to count the allocations happened during container creation with this initializer. There is also a function count that tracks number of allocations for a given initial value. It's called inside make, and its result must be stored as a Constexpr number because it will later define the array size. But there is a constraint. The array size must be a core constant expression because C++ doesn't support variable length array. What exactly is Constexpr? Is a core constant expression. If you check the C++ standard or CPP reference, you will not find a formal definition. Instead, you will see something surprising, an enormous list. This extensive list documents every case that qualifies as a core constant expression and every case that doesn't. To put it simply, they are more constant constants. Think of them as superconstants as values available at compile time. One key rule in this list states: if lifetime of object began before the constant expression's evaluation started, then this constant expression is not a core constant expression. Here the init parameter existed before evaluation began, so this is not a core constant expression. Therefore, here we cannot use the initialization value to determine the buffer size. So how do we solve this problem? To address this challenge, there was a proposal put forward to introduce Constexpr function parameters, a special syntax designed to pass arguments directly into core constant expressions. However, this proposal was initially rejected. Instead, we can use type-based mapping. Rather than passing the initializer by value, we wrote it through types. What does mapping to types mean? We define a type containing a function get that returns our initializing value. In the core constant expression, we first instantiate this type, second call method get. Now the initializing value is created during evaluation, qualifying it as a core constant expression, perfect for setting array size. And one note here, decal type refers to general concept of type derivation, not the C++ decal type operator. A current proposal accepted in C++26 aims to standardize this mechanism via constant wrapper. Under this proposal, the approach will be: first, pass your value as a template argument to a constant wrapper. Second, pass the wrapper object itself to your function. This would then allow using the original value within core constant expressions inside the function. However, as of today, constant wrapper has two critical limitations. First, it's not actually in the standard library yet. Second, it's impossible to pass non-literal types. For example, it's impossible to pass vector as template argument because it allocates memory and it's not literal type. But does C++ already have something similar? Yes, if we replace the cast operator with a call operator, we get functional object. And the most familiar one is a lambda. Here is the trick. Wrap the initializer in a lambda. The compiler then implicitly generates a unique type with a call operator that returns our value. Here is how it looks in code. First, template your function on the lambda's type. Second, pass the lambda to make. Third, in core constant expression, instantiate the lambda and then invoke its operator parenthesis. This technique elegantly bypasses the lifetime limitations by constructing the value execute exclusively during constant evaluation. It inherently satisfies core Constexpr rules that prohibit using objects whose lifetime began before evaluation. These were the key implementation details. If you want to examine the full solution, it is here. Usage looks like this. Just call a function that implements all logic and pass a lambda as its argument. For example, the concatenation of two strings in this case. We have covered how to create stud containers at compile time, but we want to create more than just containers at compile time. There are other types too, for example, regex. The standard library regex doesn't support Constexpr, but we can create it at compile time using the method I described, though we need to modify stud regex slightly. First, let's look at how a regex constructor works. I will focus on the implementation from libs to C++. Honestly, I haven't examined others yet. Imagine a string that represents a regular expression. The regex constructor parses it and creates nodes for each elementary sub-expression. The node type matches the sub-expression type. To store them as an intrusive list, they inherit from one base class, with a member that holds a pointer to the next node. After creation, when we call regex match, it goes through the node list. For each node, it calls a method that checks if the string matches the regex subexpression. This method is virtual, declared in the base class, and each node overrides this. What modifications are needed for Constexpr compatibility? First, mark all methods as Constexpr and remove non-Constexpr compatible elements. It's easy to do. We also need to wait until stud shared pointer becomes Constexpr. Second, when regex parses strings defining regular expressions, it uses locally dependent functions. The main ones convert characters from upper to lowercase and vice versa, plus a table of character flags like digit, alpha, and so on. For ASCII symbols, it's easy to make these functions Constexpr. I suspect most regular expressions use ASCII symbols only. Third, we need to create nodes via an allocator to allow swapping it for one with a local buffer. Currently, basic regex has no allocator for nodes. They are created with operator new. We cannot add an allocator as a member or new template argument to basic regex because it would break AB. However, the second template argument in basic regex is regex traits. We can store an allocator there. We cannot modify stud regex traits for the same reason, but we can create a new class like Constexpr regex traits with Constexpr locally functions and a node creation function. To maintain compatibility with stud regex, we create nodes conditionally. If traits has a node traits member, use it. Otherwise, fall back to the old method via operator new. But to store nodes in a local buffer, they must all have the same type. There are two ways to handle this: create a separate allocator for each node type, or create a unified type that represents all node types. I chose the second option. Here is how it is implemented. There is a common node type that implements the same interface and stores node implementations as std variant. Basic regex interacts with common node via the interface, and common node acts as proxy class, dispatching calls to the specific node implementation. Now, all nodes have the same type, so we can store them in array. Finally, here is the list of modifications. As I mentioned earlier, we also need to add a constructor with an allocator to pass one with a transcript. In basic regex, we only change the code that creates nodes, we leave the main logic untouched. The rest goes into the new class Constexpr regex traits, giving us a fully functional Constexpr stud regex. There are other minor details I didn't cover, but these are the main changes. So here are the final results. This solution works with containers and regex in C++20 on Clang and MSVC compilers. It doesn't work on GCC because of bug I discovered. GCC will not compile a Constexpr function that returns an object containing a pointer to itself. I believe this will be fixed in the future. What about performance? This method involves several steps, so it's worth nothing than impact. Compilation time for the file with a vector using this allocator increases linearly with the number of elements. For small arrays, it's twice as slow as std array, 200 milliseconds for std array versus 400 milliseconds for our vector. Compiling a file with a vector containing 16,000 integers takes 2 seconds. We can mitigate this by moving the container to the separate file and using ccache. As we saw, it works with std regex. Also, I tested it with an object map. It works too. Note that an object map is not currently Constexpr compatible. I made its method Constexpr and removed incapabilities, so it's worked. Memory overhead is about 200 additional bytes per container. For programs not targeting microcontrollers, this is a not big deal. That concludes what I wanted to share today. It was a pleasure presenting this insight on the evolution of Constexpr in C++. If you have any questions or want to discuss further, please feel free to ask. Thank you.